Hello. Thanks very much indeed for watching and listening. My name's Andy Purvis, and I've been asked to put together a presentation on biodiversity loss and the implications of the IPBES Global Assessment, which I was involved in for the post-2020 framework. What I'm going to be presenting is a mix of empirical findings from the global assessment and from more recent work, and also some personal opinions on some of the implications. So I'd like to start with just an illustration, an example of what's at stake. So here we've got two northern white rhinos, and these are the last two northern white rhinos, and their mother and daughter. So here we have a species that is on the brink of extinction. But global biodiversity is much more complex than just species, because the world is very complex and the biosphere within it is hugely complex. We have massive gradients of any environmental variable you care to mention, and we have hundreds of millions of years of evolution and adaptation to an ever-changing environment. So in the face of this complexity and this relative lack of mixing compared with the climate system, it's very hard to organise global information on biodiversity into a framework that makes it reasonably comprehensible. The approach that the global assessment took was to organise the data in terms of these essential biodiversity variables that are the sort of middle oval here. Distinct aspects of biodiversity, each of which is still multidimensional, but which together encompass the range of life on Earth. So, a global assessment of biodiversity has to face the complexity that, unlike climate, as I've mentioned, biodiversity isn't well mixed. So here we have a map showing species richness within a grid cell from maximum, where it's red, through to a minimum of dark blue. And this is not based on a single taxon, it's based on terrestrial mammals, birds, amphibians, reptiles, vascular plants, freshwater species as well, and then marine data from Selig et al. 2014. So this won't be perfect, but it shows how widely, how hugely local biodiversity varies around the world. And it also shows the concentration of species diversity in the warm tropics. But biodiversity is not only numbers of species. Ecological communities are species and their interactions. And those interactions make an already complex picture enormously more complex. So here, not as you'll notice in a global biodiversity hotspot, we've got a food web from Little Rock Lake in Wisconsin in North America. And the nodes here are species in different trophic levels, and then the lines are the links. And you can see the degree of complexity. If we're trying to understand how an environmental change or a human driver is going to change this assemblage, you can see how complex a task that is. And then when you look somewhere where we've got a more complex system, here's a food web of just two functional groups, leaf miners and their parasitoids, from a tropical rainforest in Belize. And again, what would happen if an invasive species came in, for instance? Well, we don't really know how a perturbation like that of a food web would ramify through. So there's an awful lot that's going to be very hard in any global assessment of biodiversity. And then as well as the complexity in terms of what it is we're trying to report on, face the fact that recording has been very uneven. So this is a map of 1.3 billion species occurrence records that have geographic coordinates in GBIF, Global Biodiversity Information Facility. 1.3 billion is fantastic. It's an enormous data set, but you can see that the dark red areas where the records are concentrated are not generally the same as the areas where species richness is highest. And this is just the geographic part of unevenness. There's also taxonomic unevenness. So here's a pie chart from GBIF on the taxonomic breakdown. And of those 1.3 billion records, 850 million, around 65%, are birds, which make up only 0.2% of global species diversity. So we actually know surprisingly little about most taxonomic groups in the most diverse parts of the world. And then adding further to the complexity, so far as we can tell, few available time series on how ecological assemblages have changed. There isn't a uniform pattern, but instead we have here the more tropical areas that are showing decreases in species richness per year on average, and the higher latitude areas tending to show more increases, the blue areas, both in the marine environment on the left and on land. So this is a spatially complex pattern, but if you look at the UK, this pair of maps give the impression that you have consistent trends. But actually, if you look as a very recent paper just a few weeks ago by Althwaite et al., if you look at the UK, where our biological recording is better than anywhere else, changes in 4 large diverse groups of organisms over the last 50 years, they don't show anything like the same trends. And if you look for a bit of that time period where the trends are parallel in all of the groups, there's a handful of years in the late 2000s. And otherwise, they're significantly different trends. So even within a region, different taxonomic groups are showing different things. So really, really complex. So how did we in the global assessment try and handle that complexity? We cast our net wide. We decided that we would take any global data set reporting on the state of nature, either relative to a pristine baseline or through time. So here as an example, I'm going to show you what we did with data on live coral cover. And there are survey data going back to the early 1970s, and they're in the panel that's shown here. It's percentage of the coral reef that's covered in live coral. And there's been a bit of a decrease, but we don't know what a pristine baseline would be like, because in the 1970s there was already damage to many reefs through human actions. However, more recently, a couple of research groups have inferred the level of coral cover on reefs 100 years earlier than that, in the 1870s. And so we're able to recast the raw data onto a scale where 100 is the pristine condition, the pre-driver state, and 0 is nothing left. When we do that, we find that coral cover now is only 53% of its pristine condition. And then that is so that the comparison with pristine tells us how much we've got left and how much we've lost. But we're also interested in what's happening right at the moment. And so to estimate that, we look at the rate of change on average since 1970. This requires another translation of the data. So now we model these data. That's what the curved line here is. It's the curve of best fit. And we rescale it so the estimate in the earliest year is 100. and we see the percentage change per decade since then. And coral reef cover, coral cover has fallen by 4% of the 1970 value per decade. So we've got these two facets then, comparison with a pristine baseline and the recent rate of change. And I'm going to talk through a few slides showing that for some of these essential biodiversity variable categories. Ecosystem structure. So the left-hand figure here is showing the recent per decade trend. And as you can see, overwhelmingly, but not in all cases, the trend in ecosystem structure has been downwards. And often it's been rapidly downwards. So live coral cover, as we saw, is decreasing by 4% per decade, but seagrass meadow area is falling by more than 10% a decade. If we look at what fraction we have left, then on average, we've only got about 53% of the original extent and condition of natural ecosystems left. So we've lost nearly half. That's ecosystem structure. The other thing I just want to mention with this is that all of these data sets are measuring the same broad facet of biodiversity, but they're talking about different ecosystems. I've summarized the right-hand figure here with a median, but you can see how much variation there is around that median. It's clear that there isn't really a single number that adequately captures what's been going on. Let's move to these populations, and here there are three scales, three levels of information that we might consider. We might get information about persistence, we might get information about changes in geographic range size, and we might get information about what's happened to actual numbers, to population abundance. So first of all, species persistence. On the left-hand side here, we see that everything is declining, but the declines are quite small. On the right-hand side, we see that actually, even at the species persistence level, we've lost a fair amount. So the top one here, Biodiversity Habitat Index, that infers the fraction of species that are able to persist into the long term with currently available habitat. And that's only at 91.5%. So that suggests that there may already be 500,000 terrestrial species, this is just a terrestrial index, that don't have enough habitat to persist in the long term, and so they're committed to extinction unless there's a fairly rapid restoration of their habitat. Let's move to geographic range size, which is a lot more sensitive because it's not just a you're still here, oh you've gone extinct measure. And here we see that mammals, the extent of suitable habitat for mammals, the bottom line here, is decreasing by about 5% per decade. That mammals have already lost, on average, about 18% of their geographic distribution, but that large mammals have lost nearly 3/4 of their geographic distribution. And then if we look at measures of abundance, we see that these are overwhelmingly declining. The exception kind of proves the rule. The exception here is the biomass of prey fish. These are fish that would normally have been eaten by the predatory fish, which are decreasing at 14% per decade. So they're bouncing back because natural predators have been eaten by us. One other one that's worth mentioning here, the top one here, we don't have this as a time series, but wild mammal biomass is only about 1/6 of what it was before human impact. And actually, if you look at the distribution of mammalian biomass in the present day, 60% by weight of mammals is made up of livestock. Of the rest, so of the other 40%, overwhelmingly it's made up of people. So 36% of the total is made up of people. And the other 5,000 species of mammal only make up 4% of mammalian biomass. One other aspect of the species persistence is how many species are threatened with extinction, and the Global Assessment estimated that 1 million species in the present day are threatened with extinction. And just want to step quickly through the calculation of that number. In order to estimate the number threatened, you need to know two quantities, the percentage threatened and the number of species. And it's slightly complicated because we're not sure that as high a proportion of insect species are threatened with extinction as other species. So across other species groups of animals and plants, about 25% of species are threatened with extinction, and that's based on IUCN Red List assessments of many groups. For insects, we don't know as much. The estimates are a bit lower, but it's very unlikely that it's much below 10%. So we've used 10% as a conservative figure. It could be quite a lot higher. Then you also need to know how many species there actually are. And there's a lot less certainty over this than we would like as well, but roughly, so there are very wide confidence intervals on these numbers, about 2.5 million animal and plant species that aren't insects, and about 5.5 million insect species. And so then you've got basically very simple, very rough maths. We've got a bit more than 500,000 non-insect species that are threatened with extinction, and we've got a bit more than 500,000 insect species threatened with extinction. Add them together, it's of the order of 1 million. We also know where these species are concentrated, and that's because of the very uneven distribution of species around the world. So here, the green areas and the red areas are both delimited on the basis of having lots of species that live there and nowhere else. So they're harmonized centers of endemism or rarity. And we know that this is where most of those million species are going to be. I'm going to move on to another class of essential biodiversity variables. Community composition, so local ecological communities, and then at a larger scale, regional assemblages. And something that's been going on through these slides, which I haven't drawn attention to up until now, is that some of these indicators can be worked out separately for the whole world and hotspots of species endemism. And so the symbols on the left-hand side show matched estimates. So the triangles are for an indicator called the Biodiversity and Intactness Index, which I'll come back to in a bit, and the black triangle is showing the global picture, and the red triangle is showing the picture in hotspots of species endemism. And so the hotspots of species endemism are where we would really hope the situation to be better than average, but it's worse than average. So for each of these indicators, the situation is better in the rest of the world than where the rare species are concentrated. If we look at regional assemblages, we don't see such a pattern of declines. And that's because people are adding species to regions quicker than we're wiping them out. If you go to a local scale, that may well not be true. We wipe out plenty of species from local communities, but wiping a species out from a whole country is actually quite hard work, whereas introducing a new alien species to a country is something we've become really good at, to the extent that the numbers of alien species, the numbers of invasive species recorded around the world are going up by over 10% per decade. What I've shown so far, distilled down to some idealised but non-existent biodiversity index, is that despite successive attempts to set targets and frameworks, biodiversity has been declining. And quite rapidly. We're losing a lot of species. We've got 1 million threatened species, and the pressures on biodiversity are not going away. So even though we've had 20 targets across 5 strategic goals, we're not going to meet any of those targets in full, according to the IPBES Global Assessment. We need to do something different if we're going to change this narrative, bend the curve of biodiversity loss, and head upwards from here on rather than continue downwards. But doing that is complicated by some limitations to. First of all, if the focus of the post-2020 framework is securing nature's benefits to people, ecosystem services, and therefore the biodiversity that underpins those, then it follows that that target should not be about extinction. Here's a simpler conceptual framework than the IPBES Global Assessment used, but it shows how ecosystem services depend largely on ecosystem functioning, which in turn depends largely on biodiversity. The Global Assessment identified 18 categories of ecosystem services or nature's benefits to people, and I've highlighted 3 here in bold because they're the ones that make up the bulk of material goods and for which there are economic markets and it's easiest to get valuations. These are also the things that we tend to manage ecosystems for, in agricultural systems, for instance. And now what I want to do is consider some really simple, blunt thought experiments. So first of all, what happens to the global supply of these ecosystem services if we lose all critically endangered species overnight? Actually, most of them don't show much of a blip. And that's because most of these ecosystem services are delivered not by rare species, but by species that are at least locally abundant and often widespread. So yeah, we would lose future options, we would lose learning and inspiration. If we lose tigers, then lots of people are going to be made very sad, but no one's going to go without food. Let's take a second scenario where overnight the populations of all wild species fell by 25%. What would happen to ecosystem services then? Well, we'd notice this. If you lost 25% of all wild species, we would have massive chaos in supply chains because we depend on the ecosystem services that the wild species do, and we depend on the abundant species for them, and we rely on that very abundance. So if we're actually interested in biodiversity for ecosystem services' sake, it's not the most threatened species that we should be worried about. And another argument that comes up with much the same point, here is a consensus view of the relationship between biodiversity and ecosystem function, whereby when you lose biodiversity from a natural system, you start to see slowly but then accelerating reductions in the rate of ecosystem functions. And you also, this is what the grey band shows, you get more variability as well. So you have less resilience. But when you're considering just a single function, there is a monoculture you could have that would deliver that single ecosystem function at a very high rate, at least sometimes. And that's what the dot on the top left-hand corner is. But over the last decade, we've come to recognise that if we're interested in landscapes that produce more than one kind of ecosystem service, then we need more and more of the biological diversity that we had to start with. And the more functionality you want out of your landscape, the more of the biodiversity you need to retain. And there's no longer a monoculture that does the job. Conversely, if the focus is on biodiversity for its own sake, not for nature's contributions to people, then your target needs to not be about ecosystem services. So here, the thought experiment is to, say, have Hawaii or Madagascar sink without trace. And we would lose lots and lots and lots of threatened species. That would blow any target you have on biodiversity for its own sake. But most ecosystem services would be essentially unaffected. So this line of thinking and the data that I've shown as well have, I think, 4 implications for having a single apex target, because there's been quite a lot of momentum in discussions over recent months for there to be a single target to rule them all and in the darkness bind them. So the first implication, I think, is the simplest, which is, for the love of God, please don't have a single apex target. I think the idea of a single apex target doesn't translate from climate, a well-mixed system, to biodiversity, a poorly mixed and probably much more complex system. And insisting on a single target is effectively climate envy. At a minimum, there have to be 2, one on biodiversity for people and one on biodiversity for its own sake. If we insist on having a single apex target, then it has to be to keep the level of biodiversity needed to provide enough benefits to people. Otherwise, we're setting ourselves up as scientists versus the people. I don't think we should do that. And if we were to do that, then there would have to be some political steer or some consensus on what enough resilient benefits to people actually means. And even then, the real target is about the resilient ecosystem services. It would be really dangerous, I think, to carve a biodiversity target in stone. And I want to show why it might actually be a moving target. So this is a modelling paper, modelling collapse in financial systems as a function of external shocks, but also the nature, the structure of that economic system. So when there's an economic shock, there is a chance of going into meltdown. There's a chance that it will propagate and there'll be positive feedbacks that carry you away into crisis. And that chance depends on the size of the perturbation, which is what the x-axis here has, but also the structure of the economy. So where you have rings, companies depending on each other in a mutually reinforcing circle, then that increases the chances, of course, of positive feedback. And that's the green line here. So even if we were able to specify now what the biodiversity target should be, doing so would risk having a target becoming out of date if the economy becomes more intrinsically resilient or susceptible to external shocks. So another kind of analogy here, it's like you're driving a car and you're driving it fast and you see a brick wall ahead of you. And you guess that that brick wall is 120 metres away. So you set yourself the target, right, mustn't hit the brick wall, got to avoid the brick wall. I think it's 120 metres away. So I will stop in 100 metres time. But it turns out it was only 80 metres away. and you just plough on into the wall because there'd be some sort of loss of face if you changed your mind. You know, the reputational damage would be too much. We have to try and stop the collapse of the global socio-economic, socio-ecological system. And I'm not sure that carving a biodiversity target in stone is necessarily the best way of going about doing that. Now, I want to move on now to implications for assessing progress towards the targets. The indicators that I started out by showing are about the boxes in a schematic like the one on the left here, whereas a model can include the arrows, well, it has to include the arrows. And that means that if your models were up to the job, and all of today's models are at least somewhat incomplete, it means that you could express everything in terms of the state, or in theory of change terms, the outcomes. You'd be able to predict the effect of choices. And although today's models aren't up to the job as much as we would like them to be, model-derived indicators are our best bet for two reasons. First, they don't need representative time series data, which is important because we don't have them, and there's no likelihood we will ever get them. And also, they can be projected forward under different scenarios, whereas based indicators can't do that. So here's a figure from a fantastic paper that came out a few years ago, assessing whether we were going to make the Aichi targets. Based on the best available time series for a bunch of indicators, all they could do as projections was carry the line forwards. There's no way, there's no basis for linking the state to changed conditions in different scenarios, because the indicators are just based on observations, they're not based on models. An alternative approach is to model how threats, how drivers influence the state of nature. Here's an example from my own lab, from the Predicts project, which I lead. This is of the Biodiversity Intactness Index, or BII, which estimates the fraction of naturally present biodiversity that still remains globally. And so this is for the year 2015, and the global average is 0.71. It, along with all of the other indicators that we could look at in the global assessment, is higher in indigenous land than in the world as a whole, but it's lower in biodiversity hotspots. And the UK is among the lowest countries for BII. So here's a map of the UK, and we're way down, really, really low. Now, of course, this doesn't mean that it would be sensible for the UK to have a target to improve its biodiversity intactness necessarily, because for all that we have very little naturally present biodiversity left in the UK, the main way that we damage nature is by exporting that damage to poorer countries with less good environmental regulation than ourselves. So I think it would be a mistake to set a purely national target without considering our effect on global biodiversity. So models let you have this level of precision in terms of where you think biodiversity is better or worse. But also it lets you make projections under different scenarios. So the IPBES Global Assessment, along with a bunch of other assessments, have considered these 5 shared socio-economic pathways. And we're able to model the history of Biodiversity Intactness Index and how it might change forward under these shared socio-economic pathways. So here's the global historical trajectory back from 900 AD, and there's the Industrial Revolution, where we see the decrease starting in the second half of the 18th century. And then a starburst when we hit the present, because we have a bunch of different options depending on how we manage the planet. And so there are sets of actions those embodied in Shared Socio-Economic Pathway 1, that would allow biodiversity to recover and would undo 50 years worth of damage by the end of the century. That's only happened one time before. If you look at the pink trajectory here, it happened previously at the end of the 14th century, and that was in response to a third of the human population dying through the Black Death. So there's a couple of ways we could do it. So to kind of summarize and extend these implications a little bit, the global assessment looked at about 80 different indicators. I'm not suggesting we should have 80 different targets, but we need more than one. And they also need to be things that we can model. The targets have to be about things we can model, because otherwise we can't test whether proposed actions by different actors, nations, businesses, whoever, actually add up to where we need to be. If the targets aren't about things we model, then our attempt to drive the global socio-economy is driving blind. Also, we're going to need a massive upscaling of monitoring. And that's two aspects to that. First of all, we need to be able to check that countries are indeed making the changes they've said they'll make. And secondly, we need good monitoring data in order to tell us what's wrong with our models. And so we can tighten this loop between modelling, making projections from those models, and then testing whether those projections are what is coming to pass. At the moment, that loop has about a 5 to 10 year delay, and that's too long. If we're trying to set targets for 2030, interim targets, then we really need to tighten up the interaction between modelling and monitoring. So, summary then. Biodiversity's decline is far too complex and wide-ranging to capture in terms of a single number. Likewise, there isn't a single apex target that can capture how much biodiversity is needed for us and how much biodiversity is needed for its own sake. If we're going to want high-resolution estimates and projections, then only model-based indicators can provide that. But only monitoring is going to be able to tell us whether we're on track to meet our targets. Both of those things have to improve, and how they work together has to improve. Because we need a planet that works for people and for nature. Thanks very much indeed.